In this video, I'll teach you how to make an AI computer vision model using Python. Here, you'll learn how to make an AI model that can classify handwritten digits all in Python. Without further ado, let's get right into it. So the first thing we'll do is go to colab.google.com. After that, we'll go ahead and create a new notebook. And once that's loaded, we'll name our notebook. You can name it whatever you want, but I'll name it Python Computer Vision. After that, click on the drop-down menu, change runtime type, and then change to a T4 GPU, save, and then connect. We're using a GPU because they're essential in training AI models. That's also why we're using Colab, because they gave you a completely free GPU for a certain amount of time. Without a GPU, training would take a lot longer, because CPUs are a lot slower in computational efficiency than GPUs. Now that we've connected to a GPU, let's go ahead and install some dependencies. First, we'll import Torch, short for PyTorch. It's the machine learning library that we're going to use today. Next, Torch Vision. It's a subset of PyTorch used for computer vision. Next, we'll import NN and Optim for model creation and training. From Torch Vision, we'll import transforms and datasets. It's used for setting up our data. After that, from torch.utils.data, we'll import data loader. It's an essential function used for loading data into our model. To reinstall our dependencies, it's finally time to download our data. But before that, I'll define something called a transform, which is essentially something that modifies our data before we give it to our model. And all I'm going to do here is I'm going to do transforms.compose and just one singular transform, which is toTensor. Models like data in numbers, so we can't give a model a raw image. We want to convert that to numbers, so that's what toTensor does. Next, we'll define train dataset. Train dataset will equal to datasets, which we imported before, .mnist. Mnist is the dataset we're using. Next, we'll set our root, which is where we're downloading it, to data, and then download equals true, because we want to download it. After that, we'll set the train partition to true, because we want to download the train dataset, and we'll set our transform equal to what we made before, which we also call transform. I'll copy and paste that, and then replace everything for the test. So I'll set train to false, and then rename. So MNIST is a 60,000 digit data set for numbers ranging from 0 to 9, and what we're trying to do is we're trying to get our model to predict, hey, given this image, what is the number inside that image? So now that all of our data is downloaded, let's go ahead and visualize our data. It's important to see what our data actually looks like because we need to know what our model is actually training on. So I'm going to import random so we can randomly select images from our data set, and I'll also import matplotlib so we can actually visualize these images. Next, I'll collect a random sample from the test dataset using random.choice. After that, I'll split our sample into sample and the label. The sample is the image, and the label is the actual number that corresponds to that image. Next, let's actually plot our image using plt.imshow. It's important to do sample.squeeze so matplotlib knows that this image does not have any color dimensions. Let's also set our color map to gray, and lastly set our plt.title to the actual label. As you can see, that's our image and that's our label. And our goal here is we're going to give the model this image and it's supposed to return this output. To finish off our data setup, let's create data loaders. Data loaders split our data into a bunch of batches, which makes our GPU more efficient and it also has less computational strain. So let's go ahead and create those by setting our batch size to 32 and defining a train and test data loader. Great, now we're finally done with data setup. Now it's finally time to create a model, which is one of the most fun parts in machine learning. First, I'll set up a class and call it net, 2 parentheses, and do nn.module in between. This is called inheritance and tells PyTorch that we're creating a model. Next, we'll create def.init and then super.init inside the def.init. And then in this init function, I'll actually define how data will flow through the model. So do self.model is equal to nn.sequential, and I'm going to create something called a multi-layer perceptron. So first, one thing I'll do is nn.flatten. This takes a 28 by 28 image and flattens that into one singular list. This is better for training because the model can take it all in at once. After that, I'll do nn.linear. In my input will be 28 times 28 because that's what happens when you flatten the flattened image. And then I'll set my out features to 256, and I'll keep on repeating that. So in and out linear, and then in features here should be 256, and then out features I'll set to 128. And then finally I'll do in and out linear, and then in features 128, and then out features equals to 10. Now 10 here is the amount of classes there are, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So essentially the model is predicting 10 probabilities, and whichever probability is the highest is what it actually thinks is the actual image. And then in between all these I'll add ReLUs. ReLUs stand for rectified linear units. And essentially that makes our data that makes the model inference nonlinear, which increases performance and efficiency. Next we'll do def forward, and we'll do self and then x. X is the actual data, and then all we have to do is return self.model and then x. And then I forgot a comma, so I'll just go ahead and put that there. Great, now we've created our model. Now it's important to test if our model actually works on the data, because if it doesn't, our training will completely break. So we'll test a forward pass. So here I'll define my model. And after that I'll pass some dummy data through the model. So the model and then torch.rand 1, 1, 2828, which represents batch data. As you can see, we see 10 values here. And then, if this was trained, the highest value here would be what the model thinks the digit is. Next, we'll do device agnostic code. We'll do device is equal to CUDA if torch.CUDA.is _ available. CUDA here is the device that corresponds to GPU, if not CPU. So this allows us to train, even if there's a CPU or if there's a GPU, we can train with whatever. And then also, we need to set our model and our data to whatever device we have, or else a bunch of errors will occur. We're so close to starting training, but first we need to define a loss and optimization. First, I'll define criterion, which is our loss. I'll set it to nn.crossentropy_loss. Our loss function essentially tells us how bad or good our model is at fitting onto the data. After that, I'll define our optimizer. There, I'll do optim.atom and then put in params equal to model.parameters. After that, I'll define something called a learning rate. I'll set it to 1e -4. Our optimizer essentially improves our model based on what the loss function says. Our loss function tells us how to tweak the parameters, and the optimizer actually does that. Next, I'll set my model to the device. This puts our model to the GPU so we can actually train using the GPU. There we go, and now it's finally time to start training our model. First, I'll set the amount of epochs we're going to train our model for. I'll do 4 epoch in-range epochs. Next, I'll define a train loss and set that equal to 0 for now. After that, I'll set my model to train mode so I can let PyTorch know that we're actually training our model. Next, I'll do 4x, y in train data loader. In this case, x corresponds to the images and y corresponds to the labels corresponding to those images. Next, I'll put x and y to our device. If we train on the GPU, we need our data to also be on the GPU. Now it's finally time to set some predictions. We'll set y hat equal to model and then pass in x. Next, we'll set our loss equal to criterion, y hat, which is the model output, and then y. This returns a number where a higher number means that the model is doing worse, and a lower number means that the model is doing better. This can also return gradients. Gradients essentially tell us how should we change our model's parameters. First, we'll do optimizer.zeroGrad to get rid of the gradients from before. After that, we'll do loss.backward to generate new gradients. And after that, optimizer.step will use those gradients to adjust our model's parameter to make it better at fitting onto the data. Finally, I'll do train loss plus equals our current loss. And then we'll do loss.item to return one Python integer, float. And then we'll do train loss divide equal the length of our train data loader. This essentially gives us the average loss over the entire epoch. Now it's finally time to test. Testing is important because it actually sees if our model is able to generalize on the data by showing data that it's never ever seen before. So set our model to eval mode to tell PyTorch that we're finally evaluating and testing our model. Next, we'll do torch.inference mode. Inference mode actually stops gradient tracking because we don't need gradients whenever we're testing because no training is being done here whatsoever. Next, we'll do the same as before for x, y, and test data loader this time. And then we'll do x.toDevice and y.toDevice. All we're going to do is put in the forward pass and then calculate our loss. That's it. Finally, we'll add on to our test loss here, and then we'll average it throughout the entire epoch. And last but not least, we actually need to print our results. So for every single time an epoch is completed, we'll print what epoch it is, our train loss, and our test loss. And once we're done with this, we can finally do the best part of machine learning training. So let's hit run and see what happens. Alright, we're done. As you can see, our train loss and test loss reduced over time, showing that our model actually learned something. So now let's actually test our model out and see what it does on one singular image. So again, I'll collect an R sample using random.choice. And then again, I'll split it into a sample and label. Now let's actually make a prediction. We'll do pred is equal to model and then sample.unsqueeze. We need to do unsqueeze because we need to show our model that this is batch data. If we give it the singular image, it'll error out. So as you can see, that's our pred, but this is raw predictions. They aren't probabilities. So let's go ahead and convert it to a probability to see what it actually looks like. And to do that, we'll use something called torch.softmax. This converts everything to a probability, and whichever probability is the highest is the digit that the model thinks the image is. Now, in order to get the model's actual prediction, we need to use something called torch.argmax. This returns the index point of the probability which is highest, which is our model's prediction. Finish this off, we'll plot our image, and we'll also plot the actual label and the model's predicted value. And as you can see, the model predicted correctly. Let's try that again. And in this case, for the number 2, the model also predicted correctly. Now let's save our model. We'll do torch.save and then our model.stateDict, which is all our parameters, and we'll set a file name. Our file name here will be model.pth. PTH is the extension that we all use for saving models. As you can see, if we reload our files, you can see there's a model.pth there. You can download that and save it for later. And that's it. You just did computer vision using Python. I hope you enjoyed this video, and I'll see you in the next one. Be sure to like and subscribe.